Thank you. Thank you everyone for coming and sticking around till the last talk. I actually wasn't too worried that I would come here and see the empty room, so I specifically bribed 2 people to come to make sure that there's someone to talk to. Okay. Is it better?
Yeah.
Yes? Okay. Did you hear what I just said? It wasn't very important, but I'll say it again. Thank you very much for coming and for sticking around till the last talk. I actually was so worried that no one would come that I specifically bribed 2 people to come and talk. I'm very pleased to see you over here. Okay, so when we talk about the classification for the stable model category today, and I'm going to use some abbreviations. So what I'm going to talk about is joint work with Benson, Younger, and Krause, who get created for PAK. And then X will be the product of the cohomology ring of my finite group scheme, and the rest you don't have information to right now. I think I'll try to jump in where we stopped last time. So the last thing I mentioned was the classical theory of Frank varieties due to John Carlson for an elementary billion P group. If you have an elementary billion P group, then X in that case is just a projective space. And then to any point in the projective space, we associate an element, equivalent element in the group algebra. We just take points and use it as coefficients for each generator. If we add 1 and generate a subgroup, it's just a cyclic subgroup inside the group algebra. And then we can take the module to the group algebra for the elementary billion P group and restrict to the cyclic shifted subgroup. And it turns out that the cohomological support variety, defined in terms of the action of the cohomology algebra on the X group, sort of global thing, can be described in this local way. We just check point by point. Take a point in the projective space, restrict the module to the corresponding cyclic shifted subgroup, and check if it's free or not. It's a very simple-minded way of describing support variety. Now there is a similar expression where fully algebras. And I think I mentioned last time, the reason we have to look at cyclic shifted subgroup, this is a very biased reason, is that an elementary billion P group is just a Lie algebra in disguise. So it tries to be Lie algebra very hard. And if you make it into Lie algebra, then this shifted thing is big. So let's say G is a shifted Lie algebra. Then recall that we, in this invariant, we see what the column of G, which is just all elements in G on which the piece power vanishes. And I'm thinking about this as a subvariety inside the linear variety G. So want to view G geometrically, the spectrum symmetric algebra rule. And this variety is given by this equation. I'll find some variety. And then I also state the theorem, that our space X for G, product of analysis, now I stated the affine version. This is a conical variety. The coordinate algebra is homogeneous. So I'm just going to project it. This is slight user notation, but I hope it's reasonable. Okay, and then we have a similar description also here. Just let me put it under the handle. Which says that cohomological support over restricted G module, and again can be one-dimensional Lie subalgebra for this element. It's restricted in Belgian algebra will be just a truncated polynomial algebra on one variable. So isomorphic to the group algebra with secret group. We restrict M to this little Lie algebra, and we check whether it's free or not. If it's not free, then we take inside support. So again, there's this local description, very simple-minded local description, only uses simplification theory, and we just check point by point. I probably should say. One thing, back to what happens in commutative algebra, so indicating there are perfect complexes or a ring, then there is this local definition of the support. So if you take complex y in here, then support can be described as a small support. So take a prime ideal in the spectrum. And then we specialize M, the residue field, and we check whether this vanishes or not. So again, it's a local description. For any point, we have this residue field, and we check whether specialization is zero. So what we're doing there is trying to mimic that local description, or to find what should be the residue field. And I'd like to do this in general for a finite group scheme. So the goal is.
Do you need to take the air pencil? Air pencil?
Of course, yes. Okay. This is the tensor triangular category. So I'm taking the tensor in that category. And if we're trying to be precise, it's y. Okay. So what we want is to realize primes in X in some representation theoretic way so that we can specialize for them. Sort of like that. We're going to do this using the notion of pipeline. For definition, J is a finite group scheme. The phi point on G is a flat map of algebras of the form K T 1 T 2 B to the group algebra KG with some field extension K over K. I'm going to abandon my convention. So I had a convention for 2 lectures that whatever K I write is the same K. It's not going to be the case anymore. I'll try to write really big K, the small K. If it's ever unclear, please ask me, but I'm going to use field extensions now. You still hear me?
Yeah.
Okay, and there's one technical condition, such that it factors through unipotent abelian subgroup scheme. We know what the uniform turbulent subgroup scheme is thanks to Michel's talks. So, picture looks like this. So I have my flat map of algebras, alpha. Just any map of algebras, flat. But it must factor with some uniform subgroup. And now this map is a map induced by a map of group schemes. So it's a map of Hopf algebras. But these two maps are just not algebras. Okay. Now, I should also point out that this group U, subgroup scheme U, is not defined over the ground field. Not necessarily defined over K. This turns out to be, first of all, important, and second of all, source of a lot of problems. Examples. Okay, so if we start with an elementary P group, and we take a cyclic shifted subgroup, if it's group algebra, then the group algebra is precisely that, and it impacts into the group algebra of P. X 1 the cyclic shifted subgroup. Then the embedding is a Python. Right, since this is just T to the P, group algebra of a cyclic group, again, we are in Cartesian. And it does satisfy my condition of factoring into a uniform turbulent thing for trivial reasons. This thing is uniform turbulent. So in fact, for elementary turbulent thing group, I don't have any condition. And the other example is of course Lie algebra. Everyone is aware of that? There isn't? J, if I have an element moved on, so the case power is trivial, then the restricted enveloping algebra of U of X isomorphic and K of X mod X to the T. Here, it's just one-dimensional Lie algebra. The universe enveloping algebra is a polynomial algebra, and we factor out the T power, which is 0. And it sits inside the restricted enveloping algebra of G, and it gives me 5 points. And one curious thing here is that now my unipotent abelian thing is here, it's on the other hand. It works for any Lie algebra. This is a Lie subalgebra. This is going to be map of Hopf algebras. And this is my unipotent abelian. So it also satisfies the condition, but sort of on the other end of the spectrum. And I can get anything in between. Now, what is the point? one piece of notation for that. So I want to go from a pi point to a point on the spectrum, and that happens in a natural way. If I have my pi point, map, and that, it induces a map on cohomology. So I start with, actually I'm going to start with cohomology of G, these coefficients in little k. Then I get to cohomology of the extended group, and then I can apply map induced by alpha on cohomology and send everything down to the cohomology of k of t mod t to the k. Okay. Now the cohomology of this algebra, we know, it's a polynomial algebra on one variable, tensor the exterior algebra. Now, we are interested in the geometry of this, so we get rid of the exterior algebra and just cohomology algebra on one variable. This is K. So this notation K of Q, tensor lambda of S. So geometrically, it's just a polynomial algebra on one variable. So what is the kernel of this map? Well, it's going to be some homogeneous prime ideal in the spectrum of cohomology. And the interesting thing about this is that it actually gives you all homogeneous prime ideals. Not all this one, this one. Here, very wide group schemes, and any prime ideal, homogeneous prime ideal, there exists pi point alpha and some field expansion such that if we take this map induced by alpha, take the kernel and take the radical, it is going to spit out P as. So this way, any point on X is represented by this map of algebras. And now if we want to do something for a module and a point, instead we just do it for the corresponding map. So we do it in the representation here side. Which is exactly what I'm going to do. Any questions? Yes?
I thought you said that the kernel of H star alpha was a homogeneous prime already. So why?
No, not necessarily. You do have to take the radical. And I think it's actually not true. Prime. I should probably say that this is where we use the conditions on both flatness and factoring condition. I want this map to be essentially surjective. And factoring to really important by doing groups can work condition. In general, it's not true. Okay. Now, once I have this representative for residue field, I can define the second support theory for an arbitrary finite. I'm going to use the following notation. curious thing that actually gave us a lot of trouble. These are naturally GK modules. But even though these are natural constructions, this is just left adjoint and right adjoint functors to the restriction functor. But they only have, so this one is okay. But the coextension actually only gives you the structure, only has the structure of GK model for a finite group scheme. You have an algebraic group in general, then some kind of module. But since I work with finite group schemes, I'm definition. It doesn't make any sense at all. Yes.
This theorem have the codimension of P can be anything. I mean, P isn't just closed, right?
Yes, that's why I have the field
And
extension.
that's why the
Yes.
dimension, does the transcendency degree of capital K over little k relate?
Yeah, basically capital P is coming to the recipe field. So I actually find this very curious what one is supposed to do here for an algebraic group, how to coextend scalars. So if anyone has seen this and knows what to do, I'd be very happy to talk about it. Okay, anyway, so we're defining group schemes of definition. We define phi support module, and we have any finite group scheme and M and G module, A and G module. Infinite dimension. And I'll state my convention. Any G module. This is so I want to define a subset in X. And I want to do it point by point. So I'm going to take a prime ideal, homogeneous prime ideal, and check if I'm going to take it inside the support. So this will sit in X. So I take prime ideal, homogeneous prime ideal with product from all. Corresponding to this prime ideal, I have my pi point. Now I have a module M, which I can extend scalars here, and then I can pull it back. It will be a module of this little polynomial algebra, and then I check whether it's free. So first I extend scalars to, okay, so this K is the one that comes in alpha P. Then I pull back. Now it's a module for K of T mod T to the P, and I check if it's free. So it's point by point check, doesn't involve any terminology. And I'm going to define another invariant, which turns out to be more, slightly more powerful than the support, FIFO support, in a dual way. So again, I take the point in approach, I take the corresponding pi point, take my module M, I coextend the scalars, and I pull it back, and I check this. And just as with the VAK support and co-support, these two things are the same. The module is finite dimensional, but they can be very different for arbitrary modules. Okay, now I can put it here. And it's very easy to check from the definition, because you just do it point by point. You restrict, the restriction is exact, and you restrict to the scale of T mod T to the P, and then you check these properties. And the forceful properties are rather formal. But then the whole point is that here we can actually check the tensor product property. So here, it has two parts. these definitions out there. Wanted to make sure I'm not going to accidentally erase them. I'm going to erase them from here. Phi support does satisfy the tensor product property. Namely, phi support and tensor n is the intersection of supports. And second, phi cosupport satisfies what all the home cosupport property or the home formula is right there. Cosupport of the internal home module, home between M and M, which is again G module, is support of M intersect cosupport of M. So cosupport actually mixes up support and cosupport when you try to compute the cosupport of the home. And it's an observation of Benson, Younger, and Crowe that but this formula actually leads you very quickly to classification of local licensing entities, if you have. Now, for something like Lie algebras, this formula is a very,
Here
very
you mix support and co-support
Yes.
on the right-hand side.
yes. And this is probably unreadable. Yes, it does mix support and co-support, which is one reason it's very interesting. Okay. Now, if we have a Lie algebra, then this property is very easy to check because we're just restricting to little Lie subalgebras. Tensor product and home commute with restrictions of Lie subalgebras. And then again, you're just dealing with representation theory of cyclic group. And all we are using is this phi. It's not very hard. If you tensor two modules over Z mod P, then the tensor is projective even though one of the modules was projective. That's it. Now this becomes a little bit more involved in general because my phi points that I use in the definition are not whole function maps. So they don't compute with tensor product and home. So you actually have to do some work. But it's possible. You can prove it. There's some very linear algebra that shows up, which I won't have any time to talk about. But anyway, this can be proved. And this invariant does satisfy this very important property. Which leads us to property number 4. Detection. Before I go there, I'd like to state general philosophy. So if you did know the detection property, then proving classification would be rather formal. General philosophy is that if we, so there's sort of steps in the proof. If we have the detection for phi support, then we will put a check mark in this one remaining row in the left column. Then from there, one can show formally, rather formally, that the BAK support equals phi support. So once I fill in the table, then actually, shouldn't have to here. I don't need. Now what this gives me is that BAK support satisfies the tensor product formula. ideals. In the small stable module K. And this chain of argument uses ideas coming from topology, which I mentioned were introduced and popularized by Rickert and were formalized in this kind of defining groups by Benson, Carlson, and Rick. So the only little thing we need is detection for pi support, detection property, and we can just follow through with this philosophy in a relatively formal way. I'm going to cheat a little bit. Now what we also want to do is to classify localizing tensor ideal into big stable module category. Any questions? So to classify localizing tensor ideals in the big stable module category, turns out that one can use co-support in the same way. So co-support turns out to be a more powerful invariant. But again, to do that we need detection property, so that one can also put co-support here and get all the same properties, except that here you'll have the home property, and ask about detection. Just here. So if we have the detection for pi co-support, then again in a formal way, we can identify co-support local cohomology functors and pi co-support. Then this spits out the home formula for VAK co-support. And then, now it was the observation of Benson and Krause that once you have the co-support theory with the home formula, then, given the formula, relatively formal way, it gives you the classification of localizing tensor ideals. In the big stable module. By the way, it's not how historically it happened, but I should have mentioned that if you have classification for the big category, then it gives you the classification for the small category. And it again shows that co-support is a stronger invariant. So in any case, if we can prove the detection property, we can do it. And this is what we'll talk about now. And let me start with a little bit of history. For finders. There are some classical theories. Two classical theories. The first one is Newton Schoonow. And I forgot to look up the year. Anyone knows? Right? Okay. In the 70s, I think. So, if you have a module for a finite group, try to be really careful when I'm talking about groups and group sheets because it's going to be important. So this is just a finite group. Then this module is M is a G module. Any module is important. Can be infinite dimensional. Then M is projective, even only if we restrict to any elementary abelian P group, projective or free for any elementary abelian P subgroup in G. Should be reminiscent of Wheelan's certification theorem. To test projectivity, we just have to test it on elementary abelian P subgroups. And then there's a theorem of Day, 78, which tells you what to do when you're already over an elementary abelian P group. So now let G be an elementary abelian P group, and M be finite dimensional module. detection property for pi support in here. Now, this theorem actually can be generalized for the support. Well, we don't have time to give an example. I'll just say. So, what we will generalize is actually Date's lemma. This is called Date's lemma. What is Date's lemma? I don't know. Of course, it's an important theorem, as usual. So, I'm going to generalize this when you find a group scheme. This is very specific to find the groups. That you can detect projectivity of any module just restricted to elementary billion P groups. No field extensions here. And for finding group schemes, it fails if you take three-dimensional Heisenberg-Lie algebra. And if I have time in the end, which I'm sure I won't, try to give an example. It's a nice little example that shows you once again how Lie algebras are very different from finite groups. Based on Schönard's theorem just doesn't work at all. But Date's lemma we can do in general. So here's here. Detection of projectivity. So G is a finite group scheme, and M is any G module and M is projective if for any field extension K over K at any pi point alpha K of T, T to the P to K G, it extends scalars of M, okay? We pull back by alpha and we check. It's a local criterion which generalizes Date's lemma since the cyclic shifted subgroups are modules. For other detection property, and projective even though the pi support M is that. I will give some credit history. So it turned out to be quite non-trivial theorem. So there are two generalizations here. First, generalization of the Date's lemma to infinite dimensional modules. And this is due to Benson, Carson, and Ricker. I think I mentioned it so many times, but I'm just going to write Benson, Carson, and Ricker. 97. Then you have to generalize to finite group schemes. So for G, a unipotent finite group scheme, this is due to Chris Bendel, the part of Sussuted under Bendel scheme. And then for infinitesimal group schemes, and then in general, identify the two pairs and get the tensor product property for the other side. Another corollary of everything this said above is that for any finite group scheme, any model, you have a BAP support equals phi of f. And basically the point here, or the most important key point in the proof, is that given all these properties, we can identify the pi support of the universal module gamma. And it's going to be P, as we originally hoped when we constructed this module. And then from here, and using universal properties, we get this more or less formal proof. And the next corollary is that actually, I'm going to use new notation. Since these two theories are the same, I'm just going to use support for them. Okay, and the corollary is that support, BAK support, satisfies the tensor product. So, you feel in my head. And once I have this, then the classification for the little stable module category, you can just fold out. You can formally do it, and this was done by Benson, Carlson, and Rickard. Once you have the properties, I'm not going to do it, but it's more or less formal. Once you have detection and you have this, it's fine. So when I move to the big stable module, this story gets more interesting. So my velocity said that if I had the co-support on formula, then again I can use formal arguments to classify localizing subcategories. Maybe before we go there, I should probably say what this classification is. I'm talking it for the third hour, and it will be really strange if I finish like number states and what classification is in after. So here's the here. So the G be any finite group scheme. There is one-to-one correspondence, or there are preserving correspondence. Between localizing tensor ideal protectors, let's say tensor ideals, in big stable model category. And subsets in Proj model. what ICRA called the support of this idea, so the union of supports of M, where M goes to all models in the standard ideal. And if we start with a subset, C and the crotch, then we take it to the category C, which is just all modules to the subform and turns out to be one-to-one. And one can specialize this to the little stable module category. And then you get it. Thick standard ideal. Are in one-to-one correspondence, the same correspondence, with specialization closed. Subset in the process. And as usual, this was proven before, so this was result in a paper for finite groups. It was done with Beth and Carson Rickard. For finite groups, it was done by Eric London and myself, but it does follow from the classification of the big stable module category. Okay, so this I stated the theorem, and I hope I made an impression that even to prove this finite result of finite modules, we use this universal modules in a very important way. We couldn't have done it without them. So infinite dimensional modules and knowing all these properties for infinite dimensional modules was essential. I was going to say two different things. Maybe I only have time for one. So there is actually a very nice, sweet, and short proof of this theorem for finite groups based on the fact that we can prove the detection property for finite groups. And once you prove it, then it's like a three-line proof for the classification based on VAK theory. So say a few words about how they should approach proof. So this formal correspondence or formal way of going there, and it's still have to do something, and we use the VAK theory. So you might remember that I had this category, gamma P, of stable module category of G, which consisted of these P local P coordinate objects, two very special objects, and secretly these objects were just trying to have support one point P. But now I have support theories, so I can just redefine it with this word. This is going to be a subcategory of all modules M, such that support of M has one prime in there. And the VAK theory gives you the local to global principle, global to local principle. Says that to prove classification, you need to show that these subcategories are classification of localizing temporary ideals it's very easy to see. They are localized in tensor ideal categories. And it should be intuitively clear that this is what we want to prove. We'd like to classify the subcategories in terms of support. P is the smallest support you can possibly have. So if you look at the category where the support is P, there shouldn't be something, anything sitting inside it. So that's what we need to prove. That if you start with any element in here, so generate the minimum localizing tensor ideal, you're going to get the whole thing. So we just need to prove minimality. And turns out that to prove minimality, if you know the co-support formula, it is literally a 3-line proof, which was going to be the only proof I do in my lectures. I think I have about 8 minutes left. So, I'm not going to do this because, unfortunately, this 3-line proof only works for finite groups because we don't know how to prove the co-support detection property without actually using classification. So we can't use it for any finite group scheme to prove classification. So we have to do something else. And we're going to talk about this something else thing, which is a piece of commutative algebra. Detection to proof. So it turns out that to show that this category is minimal, if P is a closed point, maximal homogeneous prime ideal, then you can use the co-support formula, and it's not hard. One, I want to show that gamma P, if I want to x to G, is minimal for any P. And one, if P is closed point, so it's defined over some finite extension of K, and it's just a homogeneous prime ideal, one level below the irrelevant ideal, then it is minimal. And one uses the co-support formula for that. And the reason one can use the co-support formula is that, you look at the definitions, you have a finite field extension, and co-extension and extension are the same things. So to check that the maximal ideal is in support, the co-support is the same thing. You can sort of go between support and co-support. And then, of course, we still use the co-support formula in an essential way, but just for the maximal ideal. And then we reduce everything to maximal ideals using the following here. So first of all, I need the notion of a causal object. So let's say I have an element in homology. It gives me a map from K to signature K. I can take the magnetron, just complete to exact triangle. And I'm going to call it K, P. This is also, if you know about Carlson modules, these are shifts of Carlson modules. And if I have bunch of elements, scalars to the big field K. And in this variety, the extended scalars, we find maximal ideal, a closed point, which lies over here. For M, line over P. And in fact, we can do it in such a way that M is the radical of P plus some sequence of homogeneous sequence of elements. I'm going to denotify P. Construct this ideal in a very explicit way. Okay? Then here, we're interested in this category gamma P, which is described by its universal module gamma Pk. And it turns out that here, we can look at the Joule complex, some finite dimensional module for the extended group speed, and apply the gamma m functor. And this is a module which sits over the universal module below. So what the theorem says is that the universal module for P we can obtain by taking the universal, applying this local homology functor to something above, and then simply restricting. This is the module for Gk, for the finite group speed with extended scalars, and then restrict it to G. So what this gives you is that you can transfer questions about the P point below to the questions about the closed point above. And then once you have it, then it's a little bit of freedom is what you build from what tells you that the minimality of this category upstairs requires the minimality of this category downstairs. And this is hard. Big statement. I think that's okay. Thank you.
Any questions?
Question about PowerPoint. So you need field extensions. Do you need just finite extensions or sometimes infinite?
Could you say it a little loud? Could you say it a little loud?
What?
Repeat the question.
Okay. So for type points, do you need only dk to be a finite extension?
No,
Or
absolutely not.
sometimes it
No,
needs
so
to be-
basically, if you have a primary field, you look at the rule dimension of H mod the primary field, and that's going to be the transcendence degree. So in fact, we usually look at the big transcendental extensions.
In the detection theorem, do you detect whether things are relatively projected?
Oh,
Yeah, this way.
good question.
That would be very useful.
So my impression is that sort of relative support theory is very different.
You know about the obvious guesses. You're saying that's not really true.
I don't think so, but I wouldn't bet on it.
What about the finite groups? Please tell me it's true.
Can you prove it?
No, I don't. I can use it.
I wouldn't bet on it. Think about it. Let someone else know. Frank, do you know?
What was the question?
The question is about detection of projectivity for being relatively rejected. Maybe we should talk about it.